Okay, so Dave has 24 different ways. Did anyone list all the ways for Ella? How many ways can we rearrange Ella's letters? Did anybody list them? 12 ways. So you listed them all? No, you just figured it out? Okay, well, let's list them. So we have the E's. Let's do all the ones with E first. So we can have Ella as normal, or we could have it like, whoops, like this, or we could have it like this. So those are all the ways with the E first, right? Everybody okay with that? Now if we're going to do the A first, basically we just reverse these. Those are all the ways I can do it with the A's first. If I want the L's first, I can do both L's. I can do one L. And then the other way I can do one L is like that. So 12 different ways, systematically listing them. Does that make sense? Do you notice the relationship between 24 and 12? They're half. Any ideas why they might be half? Because we have two repeating L's here. Okay, so let's list Anna and see if we can see that pattern with Anna. So we have, obviously we can write it like that, or we can write it like this, or we could write it like that. So that's all the ways that I can do it with A first, and then I can do it again with the N first. So 6 different ways for Anna. Why is Anna now half again of Ella? Because there's 2 A's, yeah, and there's 2 N's, okay? And in fact, the way we calculate it for Ella is it's 4 factorial divided by 2 factorial. So we take this 24, because we had 4 letters we're arranging, but we divide by 2 because we have 2 letters the same, but it's 2 factorial. Here we have 4 factorial because we have 4 letters, but we have 2 A's and we have 2 N's. Okay? That's the gist of what we're doing today, and it's very straightforward. So we cannot use the NPR on our calculator when we have objects that are identical. But we can use factorial. So it's the total number of objects divided by however many repeats we have. So for example, or not for example, so I'm going to show you here. And I'm going to make it a little smaller so it shows up on the screen both at the same time. Sorry. So if you have n objects and r of them are identical, then the number of permutations is n factorial over r factorial. And if you have more than one set of identical objects, so like in the case of Anna where we had 2 A's and 2 N's, we're going to have n factorial and we're going to divide by however many repeats we have of each of the different types of repeats. Okay? And we will do some examples so that you can see how, well, we'll do one specific example so you can see how it shows up, and then you'll try some in your notebook. So where we will see this problem or this technique often is with what we call pathway problems. So a pathway problem is like when we lay out city blocks. Not in Nanaimo, but in other cities, where we have city blocks that are laid out on a grid. How many people have traveled to a city where the blocks are all laid out on a grid like this? Which city, Emily? Saskatoon is like that? Yeah, Owen?
When I was in Manitoba, like every city is like this.
Right. Why do you think Saskatoon and Manitoba, they can have cities like this and we can't?
It's flat.
Yeah, right? It's just flat. You want a road there? Yep, lay it down. Straight. We are like, oh, mountain, oh, rock, oh, big hill. We got to go around, go around, go around. Okay, so we can't have them like this. But in the cities where we have flat land, you'll see it like this. Okay? So the problem goes like this. You start at A. You want to end up at B. You don't want to take any, detours. You want to get directly from A to B. But is there more than one path you can take? There is, right? There's more than one path you can take to get from A to B. You are only ever going to go, let's call this east and south. Okay, you're not going to take any detours where you do any backtracking. You're going to go in the most direct route, but you have lots of choices to go if you're just going to go east and south. No matter how you rearrange things, how many blocks do you have to go east? 1, 2, 3, 4, 5, 6, 7 blocks east. And how many blocks have you got to do south? You've got to go 3 blocks south, right? 1, 2, 3. Now you could go east, south, east, south, east, south, east, 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 east. Or you could do south, south, east, 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 south. Like you can do them in any order you want, and you're going to get there just as quickly. But the question is, how many choices have you got? A lot, right? But this is just like Anna's problem, rearranging the letters in Anna's name. Only now, instead of 4 letters, how many letters have we got? 10. And we have 7 E's, and we have 3 S's. So it's 10 factorial over 7 factorial, 3 factorial. Okay? Now, just like I said earlier when I was going over 1G, I wouldn't do this in my calculator, frankly. I mean, you can. It's fine. And if you do, don't forget to put the brackets around the bottom, or else you get it, your calculator will think you're multiplying by 3 factorial when you want to be dividing. But I would do, in my head, I would say, oh, this is going to be 10 times 9 times 8. And the 7 factorial on is going to cancel with this 7 factorial. So the 3 factorial is 6. So that's what I have. And I would either put that in my calculator, or I would do a little bit more dividing. So I would divide by 3, and then I would divide by 2, and I would have 10 times 12 is 120. Okay? Because I can do that faster in my head than I can find that exclamation point on the calculator and get it right. Okay? But your choice. I say your choice, but if this was a non-calculator question, which you aren't going to see in this chapter, so, but technically I could ask it as a non-calculator question. You should be able to do it, but you won't have to do it. Okay? And that includes the final exam. There won't be any Chapter 8 questions that are non-calculator on the final exam. Okay? Questions for me? Okay, well, I want to show you a handout with some practice with pathway problems. But I don't want you to get super excited about it. I don't want you to spend a lot of time doing pathway problems and nothing else in this section, because pathway problems are only one kind of problem that you're going to see in this section. Okay. I'll make this big, big, big. I'll make my pen narrow. Okay. You don't get too worried about the pinball problem or the checkers problem. And I can explain it to you quickly. So the pinball, this is a pinball machine. Don't you recognize it? It looks like one, doesn't it? So these are the posts. How many people have ever played pinball? They don't even do that anymore, do they? Oh, but you did it digitally, right? Not like a real one. I used to have a real one in my basement. Okay. So the ball comes down here, and it bounces off the post, okay? But the pinball's tilted down, so the ball only goes down, but the post will, depending on what angle it hits the post, will determine which path it takes to get to the bottom. So it could go like this, it could go like this, and so on. So the question is, how many ways can the ball get to the bottom? And you don't get too excited. It's only got one way to get there, okay? And it's only got one way to get to here because that's one possible path, right? Is it comes down like this. We're not talking about after we hit it with the paddles where it bounces back up. We're just talking about it's rolling down the ramp. Okay? So that's one pathway. So each of these little intersections, it's only got one way to get there. And same with on this side. It could go that way. So that's one possible path. So now we have two paths to the bottom, right? But to get here, how many ways could I get here? Two ways. Because I could go like that, or I could go like that. Now, how many ways could I go here? Right there. How many ways could I get there? 3 ways, because either one way to get there or 2 ways to get there, so that's 3 ways. And what about right here? 3 as well, okay? Now, how many ways could I get here? 4. And here? 6. And here? 4. So notice, every time I get one of these numbers, I'm adding the 2 above. Okay? And the reason I'm doing this one is to illustrate the pathway problems can work the same way. So I showed you an easy way to calculate that. Yes, Sandrine? 3 and 3 adds to 6. Yeah, okay? So altogether there's 16 ways that the ball can get from the top to the bottom. 16 different paths if you add up the 1 and the 4 and the 6 and the 4 and the 1. Okay? Now this pathway problem, we said that there would be 2 easts and 4 souths. So that is 6 factorial over 4 factorial, 2 factorial. I thought I made this really thin, my pen. I guess that's as thin as it gets here. So that is, that's better, 15 ways, right? If you do it in your calculator or do it in your head, you should get 16 ways. If you don't believe me, you can try it. Now, you can also do those pathways problems like this, okay? If you consider that we're only going to travel east and south, then we only have one way that we can get to each of those intersections because we can only travel east along there. We're not going to be coming up to there. And same with all these intersections, there's only one way that I can get to any of those intersections because I can't come from the east. I can only travel south or east. So how many ways can I get there? 2 ways. I can either go like that or like that. How many ways can I get there? 3. So notice that I'm just adding the 1 above and the 1 to the left. So how many ways can I get there? 3 ways. And how many ways can I get there? 6. How about here? 4. And here? 10. And here? 5. And here? 15. So I get the same answer by just adding up the intersections. Just like the pinball problem. Right? Each of those intersections, the 1 above and the 1 to the left, I add. Now, one like this isn't that hard. We do it the same way. We can also do it like this. What we do is we find each individual square using this, and then we multiply the 2 together. Okay? Ones like this, you can't use the formula. You have to do the counting the intersections piece. Same with ones like this where there are gaps. You have to do counting the intersections piece. Okay? The checkerboard problem, this is the checkerboard. It can only travel diagonally in one direction. So it can travel through these black ones. How many different ways can it get to the bottom and get crowned as a king? That's the question there. Okay? So that's a little different question, but it works the same way. You just add the 2 above. It works more like the pinball problem. Just in that it's nicely angled, whereas these ones are to the right and up. And down, I mean. Okay, so again, I don't want you to spend a lot of time with it. I do have solutions if you're interested and you want to try it. We can check them over tomorrow or probably the next day, actually. But today, what I'd like you to do is practice from the textbook, 8.3, because it asks you a lot more variety of questions dealing with identical objects. And then, like I said, if you have time and you're interested